All right. Well, thank you, everyone, for coming out here. It's really, wow, what a delight to see so many people involved and engaged. And I need to make a special shout out to Pyrofex and everyone who has done such a bang-up job of organizing this thing. It's amazing. I think everyone can see how professionally this has been organized. So thank you so much. And I'm here to talk about the state of the VM. And so I have to make it a little bit fun for myself because the Rosette VM is from 30 years ago. So I'm gonna talk really about two VMs and their relationship, and then I'm gonna hand it over to Keith and Tim, who are gonna walk you through some execution of the Rosette VM. I guess what I want to say is that the current interpreter architecture is actually much closer to the Rho VM that you've maybe seen me talk about on YouTube if you've been following the project. So it's actually closer to the kind of architecture that we imagine for the future. And it turns out that that's really great for coordinating software products, as we demonstrated with Microsoft's BizTalk process orchestration. It's not so great for hardware because the hardware doesn't match the abstractions as well as we would like it to. And so if we want to eventually touch base with the hardware, we need to put a layer of abstraction in between. And I would have liked to have used something different. Like it would have been great to use LLVM, for example, as that abstraction layer. But unfortunately, the concurrency story in the existing abstraction layers is almost non-existent in the sense that it's either not well spec'd or not well documented or both. And so you end up you end up in a kind of difficult spot. At least with the Rosette VM, it had a very, very strong concurrency story by design. And we had an executable spec that we could use as a target. So that's kind of the rationale for the architecture. So let's keep this live and fresh. If any of that doesn't make sense, feel free to jump in now and say, "Wait, what are you talking about?" Otherwise, I'll take the rule that silence is golden and keep moving on. Okay, so I pretty much said that. The main point on this slide that I did want to cover here is that what we've migrated towards is what's already fairly standard for the industry, which is a kind of JIT architecture, which we'll be talking about that. And I'm very excited that, it's like with a lot of things with RChain, we didn't plan it to work out to be best practice, it just did. So I want to talk about using RSpace as the basis for an abstract machine. And this abstract machine is going to be really, really dirt simple. This is the kind of thing you can walk into a high school with and explain it to them, and they can get it and start programming right away. So there are only 3 building blocks. One building block is called a name. One building block is called a value, and one building block is called a continuation. We're not going to say much more about those right now. We're just those are the 3 different kinds of things you have to have. And then you'll begin to understand a little bit about their roles and relationships by understanding how they fit together. So what RSpace says is that you can use names to point to either values or continuations. One of the consistency constraints of an RSpace database is, this is roughly correct. There's some caveats that if we dive into the details in a private conversation, we could talk about. But the rough consistency constraint actually turns out to be an old friend if you're familiar with logic, which is that you can't have A and not A. So the way that works here is that you can't have a continuation and a value at the same key. And the reason is because if you're putting well, we'll get into the instructions, and the semantics of the instructions will make that clear. So our abstract machine is going to have basically two kinds of things, right? One is going to be the machine state, which is going to be an R space, and the other thing is going to be a process pool. So I've represented processes here in this abstract way of applying continuations to values, which is what happens when you deposit values at keys that have continuations on them, or you deposit continuations at keys that have values on them. Is this all making sense? Or is this landing? Are people understanding the rough idea here? Okay, cool. So then there are only two kinds of instructions. You can put stuff, i.e. values, at keys, or you can get stuff and hand that stuff that you got to a continuation. So that now in the case of R space, the verbs are called produce and consume, but get and put were shorter ways of saying that. So that's what I used. Okay, hopefully this is making sense. So then there are, just some basic transitions for this abstract machine, right? So the basic transitions are when I encounter a get instruction, right? Then the transition, there are two possible transitions. If the key on my get instruction, so the key on my get instruction matches a key in the R space, then I have a COM event. And what that does is that pulls out this pointer pair here and uses the value that was associated with it and applies the continuation to that value, resulting in a process which is added to the process pool. Cool? It makes sense? Sweet. All right, so if it doesn't match, then we do the other thing, right? So the other thing is we would take the continuation and add that at the key to the R space, leaving the process pool unchanged. Very simple. Yes? Sweet. Now we have the dual case. Not much to it, right? If I'm going to do a put, so the instruction is put. Here's the state of the virtual machine. If there's a match on the key to a continuation, then we will apply that continuation to the value that we're attempting to put, resulting in an addition to the process pool. If there's no match, then we put the key value pair into the R space. That's it. That's the total set of instructions for this virtual machine. Now this abstract machine is not yet Turing complete. We would have to add something to make it Turing complete, namely some way. I'm eliding the issue of testing, but assuming that we have a method of testing which is essentially implied by the match, right? Then we would have to have some kind of recursion. So I'll get to that in just one second. But the nice thing about that architecture is that it works across a very, very broad class of implementations, right? You can realize this on lots of language bindings. You can realize this on lots of... I see your brow is furrowed. Do you understand? Are you following? Yeah. Yeah. Okay. All right. Cool. Oh, okay. Cool. All right. Good. Sweet. Okay. In order to do the completion on this architecture so that we do get something Turing complete, we're going to start with a simple observation. And that observation, you might think if you go look at Rolang, that every process is a communicable value. And that would be sort of the natural way of thinking about higher order process calculi. Sort of what makes them higher order is that you can take a process and ship it around as a first-class value. But that's not quite the way it works. So the way it really works is that every value is a process. So the number 5, the Boolean true, the string hello world, all of those things are values. Are processes, and then because processes are communicable, that's how, and only processes are communicable, right? This is how we achieve. This is how we kind of close the first part of the loop and get. It's our pathway not only to Turing completeness, but it's our pathway in general to enriching the language with built-in data types. That actually turns out to be fundamental when people started using the lambda calculus to do real programming. They had to face exactly the same problem, right? It's not very convenient to do arithmetic using church numerals. And so what you want to do is you want to ask yourself, what's the right way to embed these sort of natural data types into this setting? And the lambda calculus, so via Lisp, the Lisp side of lambda calculus realization and implementation, or the sort of OCaml Haskell side of the reduction of the type lambda calculus to implementation, or just ordinary lambda calculus for that matter. The trick is the same trick, right? Every value is effectively behind the scenes a lambda term, right? Behind the scenes it's a program, right? And if you ever needed to, you could ask for the lambda term style representation of that thing. So we've simply stood on the shoulders of giants and taken wholeheartedly this same idea over into this setting. And what that allows us to do is, because when in the row calculus, which you've probably seen some preface to and you'll hear more about from Kyle, when you communicate a process across a channel, what you get on the other end is its code. So it's just like what we do in the internet in the internet today, right? We ship JavaScript around across channels all the time, right? When you receive the JavaScript, it's just code until you start running it, right? So we enrich our two instruction set with a third instruction, eval, and that closes the loop for Turing completeness, right? So when I get the code back, start running it. So now I have enough instructions to do self-modifying code and do all kinds of wonderful tricks with recursion, and this is what gives me completion. Okay, so now I'm going to pause and switch gears and talk about another abstract machine. But before I do that, I just want to make sure, are there any questions about what I... Go for it.
Is there the concept of substitution, like in the pi calculus?
There is a concept of substitution, and in fact, that's what's going on. That's why I use this notation here of the application of a continuation to a value. So these continuations really do have holes in them, right? There's another way. There's an alternative presentation that Mike and I have worked on, which is a combinator view, which allows you to eliminate the variables. So then you don't have a notion of substitution. But in this presentation, I just thought I would keep it simple, so it was at a conceptual level. But yes, that's implied by the application notation here. Does that make sense? Cool. So
I've got a question on your last.
Yeah.
Is that okay?
Yeah, sure.
Okay.
Go for it.
So you've addressed what happens, like in this slide, when you're trying to put a value with a name, and you've addressed what happens when that either matches or doesn't match it with a continuation that's already present in our space. So what happens if this name actually matches, there's already a value with that name in our space?
That's a great question. And actually it turns out that that can be, you can parameterize we should defer to Henry to say what our space does right now. But it's a policy thing. So you can either replace the value, so you can have a mutation style, or you can append it to a list. So that's a parameter of the semantics. So what does RSpace do now? Yeah, exactly. Yeah, it becomes a queue, and the queue semantics is actually more in alignment with the semantics of PyCalculus. So if you reason about PyCalculus, you can see with just a couple of lines of reasoning that in the standard asynchronous PyCalculus, every channel is an unbounded queue. Right, so that's why that semantics is the natural one to pick. But thank you, you reminded me of a point I wanted to return to, which is now you can see the invariant in the semantics of the instruction sets, right? If I match when I'm doing a get on a key, then the value that was sitting there is gone, right? If I match when I'm putting a value, then the continuation that was sitting there is gone. So the instructions by their design keep this invariant for the database. Does that make sense? And that invariant is literally the computational interpretation of the law of excluded middle, which is pretty darn cool in my opinion. Okay, so we've talked about all of these pieces, so now we can kind of scooch over. So in a few minutes, Keith and Tim are going to walk through a little execution to give you a flavor of the Rosette VM. I'm going to give you a higher level view which provides some context for what you'll be seeing there. So there are a lot more building blocks in the Rosette VM. And this sort of reflects our way of thinking about computation 30 years ago. So the actor model was originally conceived by Carl Hewitt and elaborated by Gul Aga. Gul Aga consulted with us on the design of Rosette and the Rosette VM. So an actor in Rosette has 4 other actors associated with it. So this is a highly recursive, highly reflective architecture. So an actor has a mailbox where it's receiving messages, which are requests for the actor to do some computation. It has a meta, which is essentially a map of its structure. So it's a little tiny mini key value database, which says how to go from a key which an external actor might use to refer to some state inside the existing actor to an index in the actor's state. So that's what the meta does. And then there's a shared behavior object, which is the exact same thing, but it's keys for code. Very like our previous architecture, so we have keys for values and keys for continuations. Very similar notion, but a kind of refactored packaging of the idea. And then the extension is the actor's state. So that's, and in Rosette, all of those things are also actors. So they have mailboxes and metas and shared behavior objects and extensions, which also have. And so on, out to infinity. It's amazing that design can actually, in the late 80s, that design was running at 1/4 the speed of C on 1980s hardware. So Mike talked about all the tricks we used. We used a lot of tricks to make that happen. There's 2 other components which you'll see in operation in a few minutes. One is a context entity, and a context entity represents a reification of the thread of control. And sort of the Rosette's claim to fame really is taking some high-level expression, like the Rosette base language, of some computation, and shredding it down to lots of little strands of execution, and those little strands of execution are represented by the context objects. So they would be roughly equivalent to the Java thread. Actually, to be closer to, if anyone has used the Java green thread libraries, be closer to like a green thread or a coroutine, something like that. And then operations are the tags or keys that one uses in messages to send requests for computations to actors. And there are effectively two primary instructions. You'll see lots of other instructions, but all of those instructions are elaborations of the semantics of these two instructions. So there are two instructions. One is call, and that is effectively synchronous message passing. So go do this, and I'm going to hang out and wait until you have come back with a result. And the other one is send. Go do this, and I don't care what you do. Fire and forget. Okay, so those are the two instructions. So now let me talk a little bit about the state of the machine and relate that to our conception of hardware back then. The mailbox is just a queue of messages. And the conceptualization is like there's a little Maxwell's demon kind of thing sitting in front of that mailbox called a primitive serializer, right? So there are all these other actors sitting outside of a particular actor firing messages. And as Vlad was talking about, in asynchrony, the messages could be reordered, some could be delayed, right? And the primitive serializer is sitting there going, okay, you're next, you're next, you're next, right? And so it's providing the actor a serialized view of this wild and woolly cloud of messages that are arriving at various orders. And that primitive serializer implies something within the actor model. So you don't have an actor model without a notion of fairness. So what do I mean by fairness? Fairness in the actor setting is, suppose I've got a server actor and I've got two client actors talking to the server actor, and let's say that one of the client actors is very gabby, right? Very prolix, and the other one is more terse. So what you can't have in the queue of the server actor is an infinite prefix of the gabby requests before you see one of the terse requests. So it has to do with how the messages arriving in the inbox are interleaved, right? So you can't have the gabby one kind of edging out the other one. In other words, it's not possible to do denial of service in the actor model. And that's an assumption of the communication mechanism of the model. And that's kind of important. Carl Hewitt, ever the trickster that he is, likes to poke people and say the actor model is strictly more powerful, more expressive than Turing complete because it has this fairness constraint in it. So that's something to go ponder, a little bit of brain candy there to think about. Okay, so enough about the inbox. Then exactly as I said, I've just done a pictorial representation of the words I said previously. So the meta is a key value store, storing a map from operations, which are keys inside messages, to indexes into the extension. So the extension is the actor's state, what it knows about from moment to moment, right? The values that it sort of houses or contains, and the shared behavior object is a key value database from operations to methods, method bodies. So the intuition relative to hardware is you can think of each actor as kind of its own processor. Right, so the inbox is the instruction stream. The extension is the litvec, right? the data vec, and the SBO is the code vec, and then the meta is just this level of abstraction above to be able to refer to the code, the data values by some abstract tag rather than by index. It's really a very simple idea. So then the other piece of the machine state, once you've elaborated that, is a machine state is going to basically contain two things. It's going to contain a pool of threads, which you can think of as threads that are running across a collection of processors. That's the basic construction. And then the pool of threads is shredded in terms of dependencies, right? So the incoming stream of code is ripped up into a bunch of little tiny threads and how they're wired up in terms of their dependencies. So each context is going to have at a minimum the target, which is the actor that a message is being sent to, and the arguments that go to it. And then there will also be a corresponding operation that's associated with that. Right, so that's the operand. And then you build up this big tree of dependencies. So when you see Keith and Tim give their presentation, then they'll walk you through kind of the execution of a few contexts. All right. So in particular, if I hit a call, what it's going to do is to add a message to the inbox of a particular actor, and you'll see that in the illustration. So now, with respect to what we're attempting to do with our architecture, we're essentially layering the machines. There are lots of different ways that you could arrange for actors to interpret a PyCalculus-like thing. But our architecture is more resilient if we simply build a tuple space directly on top of that. Now, it turns out that it's even better if we take that tuple space and build it in as a built-in actor. It's a lot more performant. So that's essentially what's going on. Any questions about that? So I've gone over the sort of core abstract machine on top of RSpace. I've gone over the Rosette VM at a high level, and now I've talked about how we relate the two machines. Any questions about that before I move on? Yes. Can you grab a mic?
Hello. Hey, thanks. I guess the term tuple space threw me off a little bit. Could you expand on that one?
Yeah. Okay. Yeah. So tuple space was a model of computation that was proposed by David Galertner in the 80s. Yes? Oh, okay, great. So Henry's gonna give you more of a deep dive, but basically the idea it was the first key value database ever proposed. But it had some interesting properties that existing key value databases don't normally have, which was that the input is blocking, and then our refinement of the blocking input idea is that the way you block it is by passing in a continuation. Right, so that's the improvement or the variation on the idea, which is kind of cool. All right. So as you've heard before, and now I'm just going to repeat to you in pictures, when we build our abstract machine on top of RSpace, the continuation bodies can be compiled at the time that they're installed into the lower level machine. Okay? But there are going to be some instructions which are going to force evaluation later. the only other instruction I added, which was the eval instruction. Okay? So the eval instruction, if you recall, when you get a name, you know that name has got to be a process, so you can start running it. Actually, the story there is a little bit more sophisticated. We actually have some names that are not runnable as processes, or it becomes convenient to have names that are not runnable as processes. So, for example, if you had a built-in notion of a URI or a URN, something like that, you could represent it as a string and then not get as much sort of nicety about how to pull it apart. Or you could represent it as a built-in thing, but then you don't necessarily run that anymore. So you can, there's just a little bit of subtlety around that. But anyway, so that covers basically the next two slides, which is that we can compile the continuation bodies down to the lower level machine code, and then whenever the execution of these bodies hits an eval, then you have new code, and you have to potentially recompile. Right, so that's the basic execution architecture. So before I go on, any questions about that? Sweet. Awesome. It was, there we go.
Rovium better than Rosette?
Well, Rovium as a VM architecture, I think, well, hopefully, I almost want to turn it out to the group and say, use the collective intelligence. Just based on the information I've given you, what do you think are some of the characteristics? I mean, for me, the first thing, I put my architect hat on, I go, wow, that Rosette VM has a lot of moving parts, right? It's hard to reason about, right? Yeah, exactly. It was packaged in a way that made sense to programmers who were desperately trying to push object-oriented programming, trying to make sense of object-oriented programming. But the Rovium has way fewer moving parts. You can actually fit the spec on a single page, which means it becomes easier to reason about. Also, the concurrency model doesn't come with this built-in assumption about fairness, right? So I'm not necessarily assuming that I have a computational model that's strictly stronger than Turing complete. So those are two characteristics that you could just have taken straight from the talk. Yeah, maybe I'll leave it there. Do you feel satisfied? Sweet, thank you. So now in terms of the state of the machines, have I got this right, that the opcodes are nearly complete? Yeah? Sweet, okay. And the transition function is some stuff left. Okay, all right. I mean, there's lots of little subtleties that have to do with the concurrency semantics and mapping that onto, say, a thread pool in a JVM land that we're still working through. But that gives you a sense of it. There's another piece of the puzzle. I was actually surprised and delighted that the team feels that they can move to target directly the Rosette bytecode rather than the RBL level language, and then use the Rosette compiler. So if that's still the way things are shaking out, that could be quite significant in terms of execution speed, for example, because we've now eliminated one extra level of compilation, which would be quite nice. And then the nice thing about, if you've got kind of the picture in your mind of what we're talking about, when we go to self-host and emit native code, we've now got the right architecture for this, right? We've got a JIT architecture that's going to emit native code just for the continuation bodies and do what it needs to do when it hits the eval, right? Which is very exciting because our aim is to target both traditional and mobile hardware architectures. No, that's the whole point of self-hosting and emitting native code. So the idea is we get rid of the Rosette VM and the Java VM, and we go straight to the hardware. So that gives us much, much better performance. Cool. So before we take questions, Keith and Tim, you want to come up?
Okay, cool. As Greg mentioned, the Rosette executable contains two main pieces. There's a compiler that compiles RBL down into bytecode, and then there's a virtual machine that executes that bytecode. I'm going to talk initially about the RBL and how it kind of fits together, and then Tim will take it from there and talk about the bytecode and how the virtual machine executes that. Cool? Okay. So we're talking about what does the invocation of an actor look like in the Rosette VM. First basic thing is a context. Greg talked about that. It's a encapsulation of some code and some arguments and the target and everything that you need to execute that little piece of code. A context can be scheduled on a strand pool or queue or some type of scheduler that decides who executes next and whether they're ready to execute and so on. A context can have children. As Greg showed in his slides, context can have children, and conversely, the children have a parent. And the context can return its results. Once it's done executing, can return its results to its parent, which may allow it to continue to execute, and so on, and allow it to be scheduled. And obviously, a context will be able to execute when it has no more outstanding results left from any of its children. It's got everything it needs, ready to go. So for the C++ people in the audience, this is kind of how a C++ implementation of a context looks. For those of you who are not, don't worry about it. There's some data in here. We've got a program counter, which tells us where we're executing within that context piece of code. We have an outstanding that tells us how many data values are still required for this to be able to execute. We have a result, we have a target, we have our arguments, and we have the code that is associated with this context, and possibly a child context. Oh, this is the parent context, sorry. Once you have a context, the code is compiled, the arguments are ready, you install it into the virtual machine. And here we have a piece of RBL code that we're going to use as an example. It contains an operation, as Greg was talking. We define an actor, and this actor has a method, a very simple-minded method in this case, that when you call it, it returns a value of 1. Then we define an instance of the actor, and oops. So we have an instance of we've created an instance of the foo actor and called it foo lowercase. Okay. So first thing we need to do is we have the innermost actor, it gets a context, and it's told to invoke the return one method on the actor foo, the object foo, and it returns the one value. Now we're going to step it out a level, and we're going to use the return value, and we're going to add another argument to it, and we're going to call an arithmetic plus, and we're going to add the two together. So we invoke the return one method, we get its return, which is a 1. We add 1 to the result of that, and we the return 1 runs independently of any other expressions, and we call the plus operation. It's got both of its values, so it can execute, and we get back our 2 from adding this one plus this one, so on. And from here, I'm going to hand it off to Tim and let him walk you through the internals of that. So now we're stepping down a layer.
Okay, so I'm going to walk you through the bytecode. First opcode here, alloc2. It creates an argument tuple in our current context, which can hold 2 objects. And we need these, as you might have figured, the 2 objects are the numbers we want to add together. In the next step, we put the first integer into the first position of the argument tuple. Nothing fancy here. Third opcode. Here you have to know what the global environment is in Rosette, in the Rosette VM. The global environment is just a store which can store any Rosette object. Here we put a reference of the plus operation, which is also a Rosette object. We put a reference of that into the target register. It's called target register because in Rosette everything is an actor. You send messages to an actor / target. Yeah. Okay, outstanding 12.1. This one is interesting because it doesn't make sense yet here. We'll see later why we do that. But yeah, so for the install context, it just sets the program counter to 12 and sets outstanding to 1. We'll see later why. Next opcode, push alloc1. This creates a new context and installs it. Installing it means the VM now will run that new context, basically. It has an argument tuple for 1 object. And really important to note here is that the new created context here will have a reference to our initial context. The initial context will be the parent context of the new created context. Okay, so now we have a new context installed, and this new context basically in our example represents the invocation of the return one method on foo. So nothing too exciting here. We put the reference to the foo object into the first position of the argument tuple of our newly created context. We put the reference to the return one operation into the target register of the new created context. And now things get interesting. The XMIT opcode in general dispatches the arguments to whatever is in the target register. The next here means that after the dispatch, we will return control back to the VM. So then the VM will just take a look into the strand pool, take whatever context is next, and install that, and we'll continue from there. The arg1 here means it's the location where we will put the result back. So the result of the dispatch, we will write it to arg1 of the parent context of the context we just created at step 6. And here, dispatch will also schedule a new context to the strand pool. And the new context will contain the return method bytecode. So at some point in the dispatch process, we will call this method here. And what this method does is it gets the current context as an argument, and it will overwrite the code field with the bytecode of the return one method. And then it will schedule the just altered context. So at some point, the VM will get the just scheduled context from the strand pool and will run it. And this is what will be run then. And we can ignore the first opcode, it's not relevant here. The second opcode, lit1 result, will just put 1 into the result register of the context. Because we just return 1 in the return 1 foo return 1 method. And the return next opcode here, what does it do? It just returns whatever is in the result register to the parent context. And in this case, it will also schedule the parent context. And then the next tells us again, okay, just tell the VM, do whatever you want to do, basically. Okay, but why did we schedule the parent context? We scheduled the parent context because the outstanding field of the parent context was set to 1. And now we can understand why we initially had this outstanding opcode which set the outstanding field to 1. Because there was just one argument missing. Okay, so we scheduled the parent context, and at some point the VM will come back to the parent context, which here is the initial context. And because at position 4 we put the PC of the current context, the program counter to 12, we will continue at position 12 and not at 0. So everything which is left here, okay, that I just said that, is dispatching whatever is in the target register, and in this case now it's the plus operation. So we perform the plus operation, and that's it. Yeah, and then we, because of the next, we again give up control to the VM. Thanks.
So I think we're at time, but if there are any questions about what you just saw, just we can take maybe one or two. No, the 12 was just where it laid out in terms of the code, right? This is like it's basically got just a shredding of all the different little strandlets, right, laid out in a linear order. It's an interleaving, and 12 is where that final context ended up. Does that make sense? Cool. Anything else? Awesome. Thank you so much for your time, and hope you can enjoy some of the other talks as well.